Okay, thank you very much for the opportunity to speak with you today. I have a topic that's a little off the beaten track from some of the other papers, which have all been excellent, but I do have some things that actually link into that. So I am looking at trying to solve or create some tools to look at the question, are we alone? And so I'm using predictive Bayesian statistical methods as a way to maybe answer some astrophysics issues. So we kind of got into the process of doing this, or I got into the process, process of doing this. You know what? The mouse is a problem. Because in 2015, we all remember the flyby of Pluto and Charon. And it kind of dawned on me that that is the last opportunity that anybody that is alive today will actually be able to have a flyby of a new planet or a planetary body like that, because everything else is just too distant. Okay, and so we've gotten all of those big issues. And at the same time, we're seeing a huge explosion of planets, some Earth-size, some larger, that are being found. Some are even in the Goldilocks zones that are there. We've tested and visited comets and asteroids, and we're starting to have that conversation about the moon and perhaps Mars at some point in the future. And so the question goes back, well, are we alone? And so far, our visits have said, well, not really. We've been to the moon. We've kind of moved around on Mars a little bit with the Mars rover. We haven't found anything that indicates life, although we have found some water in both places. But it's so far the search for life, and keep in mind, we may not know exactly what that looks like, but we haven't found those signals as yet. And as like I said, even Mars has been a relatively barren place as well. No sign of life. So if you go back, you know, to 1960, so we're talking 60 years ago, and I've got the screen covered up with all of the, there we go, with all the pictures here. Frank Drake, who is the initial director for the SETI Institute, as he's looking out there with his large arrays of telescopes looking for some signal, proposed what is now known as the Drake equation. And it has undergone some iterations. For much of its time, it looked like this after Dr. Drake proposed it. And each of these variables, there are 7 of them that were originally proposed. There have been several others, and I'm going to show you a couple of modifications to those that I took a look at. These are all basically unknowns. And so the problem is we can come up with guesses of what all of them are, but there really is no actual known information aside from what we might find in our solar system, which I'll show may not be typical from a statistical perspective anyway. So these are what the factors were: star formation, number of what they have planets, which looks like it's going to be a big number. The planets that potentially support life, I want to go back and talk about that one a little bit more. Ones that support life, that actually becomes intelligent life, that want to communicate, okay, and then L, which is the length of the time that those civilizations might exist to send those signals. And interestingly enough, as I'll show you when I went through this one actually takes on a huge potential in trying to find communicative life elsewhere. So it's a big question. There's very little data. But the idea of using the predictive Bayesian statistics is not just the Drake equation, but we could look for Earth-sized planets. Perhaps this would be a tool to help us with Earth-killing objects, the large asteroids, the concurrent communicative life, which is the Drake equation itself, are all things that I sort of started looking at to see if there's any potential that the predictive Bayesian form of statistical analysis might be helpful. And there are people that have played around with Bayesian statistics and the Drake equation in the past. So I'm not the first one to come up with the idea, but I took this a little further. So we lack data. The distances that we're having to go find things are very vast. You know, many of the speakers before me have talked about the telescopic means we can find some great stuff that way. But again, the closest we're going to get to an actual planet or planetary type body occurred, a new one was 5 years ago, because the distances are just so large, and we find some way to magically go from one spot to another very quickly. All right, and of course, we're looking at tiny specks. So Shannon's information theory, which he proved back in 1948 on maximum entropy, which we use in the cosmology today, notes that ultimately we're going to find a range of maximum entropy over time. And so the thought was, well, can we apply that to looking for answering some of these questions? And so the predictive Bayesian form of statistics that I'm going to utilize here basically follows information entropy. So it's Dr. Press out in California made some notes as he did a lot of work on this in the 80s. And he noted that one of the benefits of using the predictive form of Bayesian statistics is we can update those. We can create a Monte Carlo Markov chain model to go do sampling, so we can do 10,000 or 100,000 examples. And as data is there, we get it. If there are errors, we can modify those based on new data, or we can solicit concepts from others to see what the thoughts are to create distributions from that. So what I've done a little bit here is I've gathered data and I've looked at, you know, what the published literature has, and I've basically done the reverse of trying to do a Delphi. So Delphi trying to go ahead and focus in on a specific number that everybody agrees to. I did just the opposite. I did this, you know, about 15 years ago on another project. And what we looked at was, let's use all of that range of data to create a statistical distribution for what people think about things that we really don't know the data for. So that's kind of the idea here. And then the concept with the Bayesian statistics is it incorporates variability and confidence within the numbers that you get. Okay, so we previously used it. I got a paper just got published using it for dose response for cryptosporidium and bacteria. I've used this for looking at wastewater disposal. I've looked at, and a few others have looked at it for a variety of other things that we've done. So the question was, well, let's go back to some things that were proposed about 10 years ago and see if we can apply this to astronomy and try to answer some of these questions. So I did pull out, this is kind of a range of estimates of prior civilizations. I'm going to come back to this, but you can see that they're all over the place. And basically these are going from the oldest ones to the most recent ones that are there. So I utilized a hierarchical predictive Bayesian model. So the idea was we would go create for each of the factors that we came up with, we would create a distribution, and we would accumulate those distributions together in an attempt to find an overall result. And that works really well if you're doing Monte Carlo Markov chains. And if you have a proposed distribution, which we chose as log normal, that was proposed previously in a paper about 10 years ago, that ultimately the Drake equation might be best answered utilizing the log normal distribution. And that mathematically makes sense as well when you have a lot of unknowns that you put in factors that you put together. So what I did, and I'm going to take a look at each of these. So I created a table. I figured out where the variables came from. I figured out a prior. In some cases, two priors if it was a bivariate distribution. Some of those you'll note are uniform, which means that we really have no information. So that's maximum entropy. A lot of these needed to be between 0 and 1, so beta worked out really well for those as well. And then I noted kind of where the source came from. The percent of civilizations that with a desire to colonize was something that was proposed by Walton in 1980. And then I have 4 of these that I discussed to replace NE in a paper I published a year or so ago. So let's take a quick look at these. So if you look for the number of stars that are formed, one of the prior authors noted that that number can be in tens to, much higher numbers. For the Milky Way, we've kind of assumed that number is relatively small. The mean from the literature that I gathered was 15.4. The range of values obviously 0 to infinity, and Dr. Drake proposed that. So this was a gamma distribution that's fairly highly skewed. So this was the PDF and the CDF for those. Likewise, when I looked at the percent of stars with planets, that number looks like it's going to be pretty big, and most of the prior estimates suggested it was either a tiny number or a big number. And this is an example of one that probably could be modified fairly easily, and I actually looked at what would happen if I said 80% of all stars had planets and used that as the average. Did it really make a big difference in my ultimate number? And the answer was no, and I'm going to talk about that in a minute. So uniform distributions in the past, beta with a mean of 0.7. Same thing when we started looking at the number of planets with life. I skipped over NE. I'm going to come back to why that is. Again, either this appears to either be common or really uncommon. Nothing really in the middle. And it depends on the authors that you had. So I actually assumed that this was a fairly small number. There was no mean, so that's why you have the distributions as they are. The percent of planets that become that have life, if you look at the literature, it's a pretty flat, uniform distribution, which is what you get. So if they would develop intelligence, so again, the answer is either that's going to be very common or it's not going to be very common. So you get a distribution at a beta that looks like that. The number of civilizations that want to communicate and looking at the length of time. So this is kind of one of those difficult things to gather. So if you go look at the doomsday discussions that are out there, the average timeline for a civilization before it somehow destroys itself or is destroyed, average is about 4,600 years. We haven't been around 10,000. You look at discussions that Union of Concerned Scientists and others have of the potential for nuclear problems, potential for climate change, potential for all these things that are out there to alter, the advance of civilization. So there are a number of things that potentially alter this. And so I used the mean coming from the literature that I had, noting that this could be in, a magnitude or more higher. And that comes into play in a big way. So again, a exponential distribution with a gamma prior. So when I looked at NE, there's a lot of discussion in the literature that if you're going to find the number of planets where life actually forms, it may have four things that are involved with it. So it's the type of star, because certain stars may not support that. They don't really have a Goldilocks zone, or they fizzle out too fast for life really to advance and form. We know it's 4 billion years and change here on Earth. If the star is only going to last 1 billion years, it probably doesn't get to that point. All right. We also looked at the size of planets, and I'm going to come back to that later. So when I looked at that was at the time, I said, okay, so we're trying to find something that's sort of Earth-sized, and the range seemed to be from half of Earth to 1.8 Earth seemed to be what the literature suggested was the right area to find. So I utilized that, and about 25% based on our solar system fall into that range. Potentially habitable zone type planets. So there were 3 of them in our solar system. Again, I used our solar system as the example. And then there was a suggestion that if there's not a moon that creates tides, all right, and so that takes a look at how the stability of the planet, so it doesn't just face the sun all the time. So that moon was kind of important. So I took those things out there, and note that there are some data points to support all those. The literature suggested that NE was actually about 2%. And when I put all these factors together, interestingly enough, it came up to be about 2%. So utilizing these factors seemed to work out. And so that's kind of what each of those looked like. Again, beta distributions for the most part, because they're 0 to 1. And then the C factor was the interest to actually colonize and travel and get off your planet would be an option as well, because you're not going to find life if it doesn't travel or you travel. And so that was kind of the concept that Walton had for this. And they proposed a beta distribution with uniform priors, which is what I did. So if you look at the mean of 10,000 samples when he went through it, these are the means that I got. And then we looked at a target distribution with the MCMC with a Gibbs sampler on the backside, usually utilizing these as the hierarchical factors. I came up with an average of 24.64 when you put these together, but that is a little bit misleading. Because ultimately what happens is that you get a distribution like this where you have very low probability for a long period of time, and then suddenly it kind of goes upward. And so what you find is that, you know, basically these are all zeros because something happens, life doesn't form. And so in looking at the galaxy, the Milky Way galaxy alone, the probable number of concurrent life as an average was this 24.64, but the actual number, the 50 percentile value, was actually 1. So it's they would be basically that we're alone. Was this scenario though, and then a little over 50% you get into 2, but it's a very small number until you get about 98%, and then it starts to creep upward relatively quickly, and you get into the thousands when you get in the 99.9 percentile. So the answer really comes up as a nice statistical method. This was the data that we might actually have, the subjective data that we had. And then what I did is I looked at what were the factors that would make a difference. So I looked at each of the factors. Obviously, the ones that were between 0 and 1, I couldn't change them by a magnitude, so I either multiplied them by 2 or divided them by 2 or some number like that. And for the most part, they didn't really make any difference at all. You couldn't really tell the difference. The thing that made a difference was L. So if L is 49,000 as an average as opposed to 4,900, what you find is that you increase the number of concurrent civilizations in the average by 10, which is exactly what you'd figure. It is the factor that adjusts this number. So, 99 percentile value probability is there's less than 100 civilizations. Had to get over 1,000, you had to go to 99.9. All right, as I said, L was the big factor that did that, and there's a 5% chance that we might be able to communicate with 1,000 different civilizations. There was no chance that there was 100,000. It never, the graph, 10,000 times, 50,000 times, I never got to 100,000 civilizations. So that was kind of a cool answer. So if I looked at the 25, it's within this range right here that the others had, kind of on the low end. But at least it says there is a potential possibility. So it's not huge. So the next thing I thought about doing with this was I wanted to go back to the Earth-sized planets. And there's a recent thing that came out that said, it estimated, this is like last week in Science News, I think, it said they thought there was 300 million Earths out there in the galaxy. And I had kind of looked at this before. I've been playing around with this a little bit. So what I did is I used Pareto as a graph to try to look at planet size. Pareto is useful for incidence size, actually we used it for the bacterial thing as well. So I've used it for a number of things. It's used for income, and it creates a very, very skewed distribution. All right, so I went out there, and if you can look at the line, basically the Pareto parameters are based on a log-log graph. So here's the log-log graph, and so the value of A in the Pareto 1 is 0.1512. And so you go back out and then plot this, you get a number that looks like this. It gives me a quick hint that there's an issue here. But I'll look at, I plotted everything that was more than 1 to the 15th kilogram. I think that 1 to the 15th may be a break point, and I'll show you why. All right, and I did note that the solar system may be atypical. And so then what I was looking for, so here's the backgrounds. What I ended up finding was that the average value in the 5,000 I did was about 0.75 compared to our solar system having 2 Earth-sized planets. And I'd had some discussion with some folks, and the idea was, well, okay, so our solar system may be very atypical, and yet it's the only data that we really have that we know for sure. Okay, and but actually the statistics would indicate that perhaps we are atypical, since it got less than one Earth-sized planet in a solar system. So then I went ahead and looked at finding Earths, but if you're at 0.75, when you look at this graphic here, you can figure out that there might be 1.4 billion Earths, which is about 4.5 times what the most recent number was. I haven't gotten into their data because it just came out. But the reality is it's not horribly out of scale on that estimate. So potentially the predictive Bayesian statistics with a little more work, and looking at perhaps the cutoff should be before the 10 to the 15th number is something that we should evaluate. So then I decided that let's take a look at much smaller objects, and let's look at objects that potentially could impact Earth and create a problem. Okay. And so I went ahead and did that. Again, I went ahead and applied the Pareto version to that, and we have a problem. And I played around with this fairly considerably, and the reality is there is no relationship between the number of large-sized objects in a solar system and very small-sized objects. There's just no way to make those two things work out, and I've been kind of playing with that for about a year now. And so it suggests, based on this graph, that there is a scaling issue. And I think if you start looking at stars, there's a scaling issue there as well, perhaps, between smaller stars, and we're just looking at mass, and bigger stars or things that are larger than that. And so an area, well, one of the things I'm going to play around with, but I think it's an area of interesting evaluation, is regardless how much I went ahead and changed various factors associated with the Pareto priors, I never could get anything close to the incident size that you would expect to find. And it is clearly a scaling factor, and you can see these two graphs might sort of go together if they weren't off by, a factor of, 20. So the idea coming out of this was that I think the predictive Bayesian methods do permit some opportunity to use subjective data, things that we're finding or things that we suggest in a good conversation out there to help us analyze and maybe look for things that might answer bigger questions. So if we're looking for Earth-sized planets, where are we going to find them and what do they look like? How many of them might there be? And then also if we can figure out which stars. So the application looked like it worked pretty well for the Drake equation. I'm not sure how well it's worked for the number of Earths, but at least it's within the right magnitude. But when we start looking at very small objects, there's clearly a point where that doesn't work utilizing any extrapolation from known objects. So you're really looking at number of unknown objects that's unknown with an unknown distribution. So it creates a much more challenging question. Why do you want to get to small objects? Well, is there a potential that we can figure out how the scaling factor changes? And if so, does that help us to get to really, really small things? Like, does it point us to what we should be looking for dark matter from a size? Does it look at really large things from a size if we can figure out how the scaling changes between each of these regimes? So are we alone? Well, the Bayesian statistics indicate we might be, but then again, there's a potential that we're one amongst many. And we might be able to use these concepts for searching for other Earths and asteroids as well. And with that, any questions?
Thank you, Professor Bloetscher. That was lovely. That was very interesting. I was going to make a comment, and that is Frank Drake is a dear friend, and he was a professor at UC Santa Cruz. In fact, it's after he decided to retire that UCSC hired a couple of new faculty, and I was one of those new faculty, but Frank has become a very good friend over the years.
Excellent. Excellent. Yeah, I know he's still around because somebody asked me when I put the paper in Astronautica a year ago. They said we should see if he wants to peer review it. Like, yeah, good luck with that.
Right. So. No, the SETI Institute is not far from where I live in Mountain View, and I see him out and about from time to time.
Excellent. That's great.
Thanks for a very interesting talk. All right,
Does
other
anybody have any
questions?
questions?
Please go ahead.
I have a question.
Sure.
So I think, thank you again for your presentation. It's neat. And I teach some of the intro astronomy courses, and this topic is always very popular. I'm wondering if you have any thoughts on some of the more exotic ways of detecting life, whether you're looking for Dyson spheres or, you know, is there any sort of possibility of searching through data that we already have on hand and finding some hidden gem?
Yeah, I would suspect there was, and remember the Drake equation is, communicative life, that we would sort of recognize that we would go to, and you'd have much, what would happen if we just said life as opposed to intelligent communicative life. It's one of the reasons why I think it's so exciting to look at the the search for water, because our idea is if there's water or if there's methane, that might be an indicator that there's life out there, right? And methane being an off product of bacteria. So I think it's kind of cool, and I think the real question that we have, Dr. Spencer, is, what is the life? What does it look like? And we're assuming it's carbon-based and water, and and the methane is a tracer and some things like that. But what if it's different? And so if you had, perhaps if we got outside the 0.5 to 1.8 Earth-sized masses, would you need to be heavier? So and so would there be a different structure? Years ago, I remember somebody saying, well, what about silicon? Because it's sort of like carbon, but okay, but you could have something that was a very different structure. And is water the only way to transmit things? Well, maybe not. And I think that's a really cool, and I'm not a biologist, but I think that's a really cool question to ask, is, if we found it, would we know it when we saw it? Because it might not be in any way, shape, or form what we expect that life to be. And I think that's the other thing too, is we have, you have all the movies out there about all cool life and ET and all that kind of stuff like that, popular stuff. But I think you're much more likely to find bacteria. And who knows whether that's a good thing. I know that's why they spend, I know Steve Swanson, who's at Boise State, he's actually an alumni from, alum from FAU. And he's come to talk to us, and that's one of the big things when they come back from the space station. If they've been out on walks and stuff like that, it's basically decontaminate us, because making sure that there's not some weird thing that comes meandering on in, I think it's less of an issue at the space station than coming off the moon. But there is that question, what if you bring something back? We would have absolutely no ability to deal with it, because we've never seen it before. Little unfortunately like COVID. So
I've heard Don Jennings at Goddard joke that to search for life, you want to search for Freon or something ridiculous that wouldn't happen naturally. So I think that might be fun as well. But yeah, do you have further comments on the contamination of the moon? I remember seeing something about a year ago that there was a problem.
No, not really, because, and I'll be honest, I have not dug through some of the data. If somebody's interested in collaborating on on evaluating some data, it would be kind of fun to see if we could learn more. And a lot of the Drake stuff, I'll be honest with you, I've been working on that, for years. It's not a funded project. It's a interest. So I've worked on it for some time, and one of the things I noticed is, we're just all of a sudden starting to see big changes in some of those factors. We're understanding more about stars and the star type. I think we're pretty comfortable that most stars have planets around them. So there's at least 3 of those factors that I think we got some pretty good confidence on. I tried to build that in a little bit. But then, what does intelligent life look like, and how long does it take to go? And Star Trek sounds great, but I don't know that the civilization lasts, 20,000 years, right?
Yeah. So on that happy note, Sorry, I was going to say on that note, I'm going to cut off this discussion because we're running a couple of minutes late now. So
Okay.
I was going to hand it back. Thank you so much,
Thank you.
Professor. Thank you.
I think
My pleasure. This is great.